In this example video, we will find limits by using different theorems. In example 1, we are asked to use the theorem on real and imaginary parts of a limit to evaluate this one. The theorem says, suppose that the complex function f is defined in this way. That is, f of z equals u plus iv, where both of u and v are functions of x and y, and z equals x plus iy. And also, we suppose z naught equals x naught plus iy naught and w naught equals u naught plus iv naught. Then this limit will be true. That is, limit of f when z approaches z naught will be w naught. If and only if these two limits exist. Coming back to our problem, we see that f of z equals z square plus I, and since z is x plus iy, after squaring and rearranging all the terms, we get x square minus y square as the real part and 2x plus 1 is the imaginary part. So in this way we get our u and v for this problem. And also here z naught equals 1 plus I. So we get x naught equals 1 and y naught equals 1. Now we will find u naught and v naught in order to get w naught, since w naught is the ultimate limiting value of our given function. So we apply limit on u. Since x naught and y naught is 1, so x approaches 1 and y approaches 1, and also we found u is x square minus y square. So applying the limit, we get 0 for u naught. And same procedure will be applied for v naught. So we apply the limit on v, and we found v is 2xy plus 1. Applying this limit, we get 3, which is v naught. Since w naught equals u naught plus iv naught, so we're replacing the values, we get w naught equals 3i, and this is our answer. In the following two problems, we will apply the properties to find the limit. So have a look at the properties. Here we consider the limit of two different functions. One is small f of z and other is capital F of z. And the limiting value of first one is w naught when z approaches z naught, and the limiting value of the second function is capital W naught, and also here z approaches z naught. So let's go back to our problem. In problem A, the function f of z is in rational form. Here, both the numerator and denominator are polynomials. In such case, it will be wise to find the limit of each and every term separately. And then we get the limit of the numerator, which is 4 plus 3i. It will be easy for our further calculation if we keep this result in a plus ib form, which is the standard form of a complex number. And in similar way, we also find the limit of the denominator. Here, one thing should be noticed, that the limiting value of denominator is non-zero. So, by the quotient law, that is, the limit is applicable for both of the numerator and denominator, we get this one. Also, this one is in rational form. So, we apply the rule for division of two complex numbers. That is, we multiply both the numerator and denominator with the conjugate of the denominator. And finally, we get this. We will keep our answer in this form since this is the standard form of a complex number. In problem B, f of z is again in rational form. So we will find the limit of each and every term separately. Here 4 is a constant, so after applying the limit, it will remain same. And combining all the limiting values, we get the limit of the numerator is 0. But the limiting value of denominator is also 0. For this reason, we cannot apply the quotient law here. In such cases where applying limit, the denominator becomes 0, we will not apply the quotient law for limits directly. We will try to factor in the numerator or denominator. Here, the numerator can be written in this form also. So from this part, we get z minus 1 whole square minus, and 3 can be written as square root of 3i whole square. We rearranged this in such way so that we can apply the formula a square minus b square. Say this is a and this is b. So we find this form. Now, using the new form of the numerator, we can see that these two terms can be cancelled, and now we can apply the limiting value, and finally we get our answer. We usually apply this technique of factoring in such cases where for the given limit the denominator becomes 0